Hi everybody. Today what we're going to work on is a lab looking at blackbody radiation. So in Schoology, in the chapter 3 and 4 folder, you're going to find a folder for labs, and then you'll find this blackbody radiation lab. In here there's a copy of the handout that you have, as well as a spreadsheet that'll help you do the last part of this. So what we'll do is open this up, and within this, all we're going to need from this is the link here. So you can click on that link. It'll take you to um, the University of Colorado Boulder website with lots of simulations. This one's going to simulate the black body curve of different objects at different temperatures. So what are we looking at here? Right, we've got our wavelength on the x-axis and our intensity, our brightness at those particular wavelengths on our y-axis. And we've got a magnifying lens that we can zoom in and zoom out on the y-axis or the x-axis, which is going to come in handy when we get to higher or lower temperatures. Also up here we've got the relative amounts of red, green, and blue of the visible part of the spectrum, and when they combine, what color would that object appear. So this object here is roughly the temperature of our sun, about 5,800 Kelvin. And if you notice, its peak is kind of right in the middle of the visible part of the spectrum, and oddly enough, it's kind of peaking in the green. And you look up at the sky and you see some blue stars, and you see some red stars, and you see some yellow stars and some white stars, but you don't see green stars. And why is that? Well, when it comes down to it, we're putting off roughly equal amounts of all of the colors in the electromagnetic spectrum that we can see. And you mix those of roughly equal intensities and you end up with white. If the sun were cooler, if you notice, the peak is getting lower, so the brightness is decreasing, as kind of shown by the little star up here. And then also the color is shifting more towards kind of the red end. If you look at our peak here, it's kind of right in the red, but it has some blue and yellow and green in it, so it's going to kind of make it a little bit to the left of red, so kind of an orangish color. If we get down kind of even lower, and this is where the zooming kind of comes in handy here. So now it's really tough to see where that peak is. So if we just kind of zoom in on here, this peak would be in the infrared. Well, how do I know that? I can go over here and look at the labels, where we've got our visible part. To the left will be ultraviolet, to the right will be infrared, and kind of in the middle is going to be our visible. And if you look here at our temperature, relatively low, 2,700 Kelvin, which is still very hot, but in terms of intensities of stars, a pretty cool color. So really there's very little blue light coming out of there, a decent amount of green, a bunch of red, but again our peak is over here in the infrared. So this might be like the filaments inside of your toaster when you're waiting for a Pop-Tart or some bread to come on out. Well, I guess the bread would go in, toast would come out. Anyway, um, even lower, here we're getting into the temperature of us. It doesn't, about 300 K is about room temperature, and it looks completely flat here. But if we zoom in again, there we go. If we zoom out over this way, um, you know, objects in the room around you, they are glowing, but they're glowing way in the infrared, uh, and really not giving off any visible light. That's why you turn the lights off, you're not going to see anything glow. Um, the other thing we're going to want to put on here is our graph values. So this gives us an idea of how bright, which for this lab is not super important. Down here, what we want to see is our wavelength. All right, so what are we going to be doing with this lab? And here it's going to ask you some questions about like changing the temperature and what you see from that, as well as down here it's going to ask you to find your peak wavelength. And if we go over here, at different temperatures. And for that, really this is the number we're looking at. We can zoom back in or zoom back out as we change our temperature and see what our wavelength is at the peak of this curve for different temperatures. So you can carefully adjust the value here, zoom in and zoom out as needed, and then you'll put those in this data table here. It's going to ask you to make a plot of temperature versus wavelength, and this is where the spreadsheet comes into play. So let me open up that spreadsheet. And what you'll want to do is download this. And I'm going to open it on up. And I've got this formatted so that when you plug in those wavelengths that you get from the lab, it's going to automatically graph it with the particular temperature. So I'm going to put in fake numbers in here. So let's say, whoops, I need to let in here. Wavelength is going to be really long here, so 270. Again, these are numbers that are all made up here. And it's going to give me this kind of inverse relationship there. And at the same time, we're going to make another graph, and that's basically converting these wavelengths to frequencies, which is just the inverse of your wavelength. So what I've done is I put a formula in here to divide 1 by the number that's in this cell, divide 1 by the number that's in that cell, and so on and so forth. And it graphs it. And I think this box might be slightly out of place, but really what we've done is we want to find the slope of our best fit line here. Oops. And that slope, if you do it right, which should, will give you the value for the constant in Wien's law, which is what this lab is looking for. So let me go back down here. Oops. So once you do that first graph, it's going to automatically make your second graph. It's going to come up with your slope in there, and that's going to be the value for Wien's law. Basically, it's like a fudge factor that allows us to compare temperatures and wavelengths. And the idea is, with stars, one of the things that we can tell from just receiving the light from them is their temperature. If we look at the spectrum of light coming from them, we can find out what part of the spectrum has the greatest intensity, basically where its peak is the highest. And if we know its peak wavelength, we can convert that to a temperature. So that's how we know how hot stars are without ever having to go to them. So, but that's what we're going to be doing for this lab. Once you do that, I think it asks us, there we go. So Wien's displacement, we're going to find this value. Let's see, wavelength is equal to, we're going to try to find out the slope of our line should be close to 2,900 micrometers. And we're going to look at our percent error. And if you haven't done a percent error formula, basically you're finding the difference between the real value and your value. So take the experimental value, the one we got from our graph, minus this 2,900, and then you'll divide that answer by 2,900, and then you'll multiply that by 100 to get a percentage, and then that's your percent error. So, but that's kind of what we're going to be doing for this lab. So I'll end this video here, and if you have any questions, feel free to send me an email or a Schoology message. Actually, probably a Schoology message would be better, because I get, on my phone, I get pop-ups on that. I got the the notifications turned on, whereas my email I have to go in and check it every couple hours or so. But that's it. Hopefully this works for you. But again, like I said, if you have any questions, feel free to reach out. All right, have a good one.